So at the end of the last video we were talking about the challenge of going from alternating current. Here we see the alternating voltage, the changing positive and negative voltage of alternating current. Going from that, which we get out of our PowerPoints, to something that we can use in computers and electronic devices, which is direct current, okay, DC, which has this continuous voltage, single voltage, unchanging, and means a constant movement of electrons all moving in the same direction. Let's discuss a little bit more the differences between these two graphs. So there are actually three things that we need to tackle when we're converting from AC to DC. The first thing is the size of this voltage, okay? The maximum voltage here in AC that we get out of the PowerPoint is usually about 240 volts. Okay, so that there could be 240. But the voltage used by a lot of electronic devices could be much lower. It could be 5 volts, it could be 12 volts. Okay, so this might only be 12 volts that's required here. So we want to transform this high voltage into a low voltage. So one is transformation. Of the size of the voltage. Another thing that we'll observe is that, alright, so here we have a positive voltage, here we have a negative voltage. That means that the current in AC is obviously alternating. It's going backwards and forwards. We don't want that. We want to be able to have current, a voltage that's always positive, so that current is always moving in the one direction, as in DC. Okay, so we need to eliminate this negative part of the graph there. So we need to achieve a single direction of flow. Okay, so that's one thing that we need to achieve as well. And then the other thing, the final thing, is that this value is changing. Here we have a low voltage, here we have a high voltage. Low again, high again. Even if we manage to get rid of this negative section here, we'd still have a changing voltage. But we want a continuous voltage. Okay, so we want to smooth to continuous value. These are the three things. We want to transform the size, we want to make it move in a single direction, the current move in a single direction, and we want to smooth to a continuous value, so it's nice and flat like in the DC. Okay, so let's look at the first issue, the one of transformation. We want to take this 240 volt signal that's coming out of our PowerPoint in the wall, and we want to convert it into something a bit more useful. Say 12 volts. We'll take that challenge first. We want to reduce it by a factor of 20. Now this is a challenge that these sorts of things, alright, these little adapters that you have for plugging in and powering up your phone, face all the time. And how do they do it? Well, if we take the back off this one, and I'm not recommending that you do, we can see a few different components. These ones down here you might recognise as diodes, and we'll talk about them a bit later. This one here is a capacitor, a large capacitor, and we'll talk about that a bit later. And this thing here is called a transformer, so as you might guess from the name, that's what does the transforming of this voltage from 240 down to a maximum of 12 volts. Okay? Now, how does it work? Well, just a moment. Well, it just so happens that it's actually quite easy to convert an alternating current of a particular voltage into an alternating current of a different voltage. And in fact, that's the reason why we use alternating current to transport power long distances. That's why you have alternating current in your house, and you don't just have a direct current outlet that you can plug directly into. Alternating current can be converted to a very, very high voltage, such as is transmitted in your overhead power lines, okay, and those really, really big power structures that you see out in the country, for transmission. It's actually more efficient to transmit at a higher voltage. We'll talk about that in term 4. But there is a very simple and neat way of converting from a high AC to a low AC. What happens is you take a piece of wire, okay, like this, and you wrap it around an iron core, like this, okay? Actually, in reality, you do it a lot denser. You don't use an Ethernet cable, but whatever. You have a lot more wraps of a very, very thin wire. And what this actually does is this creates, when you feed an alternating current through this wire, creates an alternating magnetic field. And then if you get another completely different piece of metal with a bit of wire wrapped around it and you bring it close to your original wire, the alternating magnetic field created by the first wire creates an alternating current in this second wire. So if we go to a diagram now, we have an input voltage, alternating voltage coming through this wire here. We have another coil of wire nearby. This alternating voltage creates an alternating voltage and an alternating current in this coil. Okay, so we'll get some output voltage which is related to the input voltage. So this is what a transformer is, and this is actually what this item here is. It's two coils of wire wrapped around a metal core very close together, okay? And we have an input voltage and an output voltage. You notice that these aren't actually directly electrically connected, okay? There's no direct connection between there. It's the magnetic field, the alternating magnetic field, that causes the connection. We don't actually have to understand how that works, that process, which is called induction, understand how that works until we study it again in second semester. But what's the relationship between this input voltage and this output voltage? Well, if we think about what things we could possibly vary about each of these coils, the main thing that we can vary is how many times we wrap that piece of wire around the metal core. And actually it turns out that it's the relationship between the number of wraps on this side and the number of wraps on this side that determine the relationship between V in and V out. So if we have on this side a certain number of wraps, N1 equals number of wraps, and we have an input voltage of V in, then on this side we have another number of wraps, I'll call that N2, and we have an output voltage, V out. Is the output voltage, okay? Now, the relationship between the input voltage and the output voltage is given as V in over V out equals N1 over N2. So the ratio between the output voltage and the input voltage is actually the ratio of the number of turns on the input side, N1, against the number of turns on the output side, N2. The next thing I'll show is an example of how that can be applied, that formula can be applied. I did have two examples that I tried to attach to the end of this video, but it was too long, so please see the examples and the summary in next video, video 3.